Hi everyone, I'm Darshni Ramu. Today we would like to talk about breach defect assessment from integration of UAV thermal sensors and acoustic emission. The introduction of breach defect assessment. Firstly, damages in breach do happen commonly. For that, surveyors do monitor the breach structures from time to time. Today, we are going to see breach monitoring using UAV thermal sensor and AE emission. Definition of thermal sensor. Thermal sensor measure the relative surface temperature of objects. When long-wave infrared radiation emitted from objects strikes the thermal sensor, it heats up the microbolometer and this changes the electrical resistance. This changes the converted to electrical signals and stored as raw data or processed into thermal imagery. Acoustic emission technique. The AE monitoring process requires a material deformation which is used as the source and transducers to capture the stress waves that are generated by the source. AE sensors are the heart of the AE systems as they transform wave into electrical signals. In the case of non-integral sensors, the signal is amplified before transmitted to the AE instrument, whereas for integral sensors with an embedded amplifier, the wave is directly transferred to the AE instrument. Now we're going to see the development of the technology. Firstly, UAV thermal sensor. The smart sensing tool including cameras, drones, smartphones and robotic sensors for supervision, retrofitting and management of large-scale structures. Another study presented the UAV practice adopted for the United States breach inspection programs. The building inspection using thermal imaging aided by unmanned aerial system. The construction applications of aerial system, particularly their viability in building maintenance and inspection, damage appraisals, site renaissance, and progress monitoring. The table shows the scope of the study. Here is the mind map where UAV enable remote sensing applications for breach conditions assessment. Next, acoustic emission techniques. The applications of AE is reinforced concrete RC structures in order to assess damage due to fatigue loading and concluding the AE analysis, such as AE parameters, intensity analysis, etc., are limited, whereas the application of AE in structure with increasing fatigue magnitude needs further consideration. Appropriate AE sensor types are important in the fracture monitoring of concrete structure, and since concrete is a highly attenuating material, lower frequency sensors are most suitable. Applied to AE sensor together with multi-channel monitoring and operating in order to study cracking in crumpled rubber concrete. AE can allow for a good understanding of micro-cracking and fracture monitoring. Prefabricated structure elements were assessed and AE features provided information for concrete cracking, bar debonding and bar plastic deformation. The figure shows examples of AE sensor application for crack monitoring.
The slide above show the objective for the project 2, which are to aim to assess breach defect and its behavior when defectness happen using the function from acoustic emission. The second one is to set up usage of UAV thermal technology, especially by using DJI Phantom 4 and applying it on detecting any defectness or dullness from the breach. The third one is to construct a condition where defectness of the selected breach can be observed through the process of unmanned aerial vehicle thermal imaging. The theory of concept of using UAV. The earliest recorded use of an unmanned aerial vehicle for war fighting occurred in July 1849 by using hot air balloon. But nowadays we are using UAV. The using of unmanned aerial vehicle UAV is one of the effective aerial components that used on defect breach by recording the image in linear line in stereoscopic vision along by the breach in infrared mode. As you can see by the picture beside, you can see that the color of the plants can be detected as in red color in infrared mode that recorded by UAV. And infrared mode on the breach recorded by UAV show the defectness of breach affected by growing plant. Next one is the theory of concept of acoustic emission. Acoustic emission is defined as the formation of transitory elastic wave following the rapid release of energy from localized sources within a material. The detection and conversion of these high-frequency elastic waves to electrical signals is the basis of the acoustic emission and heating technology. This is accomplished by directly linking piezoelectric transducers to the structure surface and loading it. Sensors are fastened to the structure with tape, adhesive bond, or magnetic hold-downs and are connected to the structure with a fluid called plant. During structure loading, the output of each piezoelectric sensor is amplified by a low noise-free amplifier filtered to remove any unwanted noise and then processed by appropriate electronic equipment. When more than one sensor is employed in the defect breach area, the acoustic emission source, and as a result, the problematic area on the breach can be detected. The location is determined by measuring the signal arrival time at each sensor, which is based on wave propagation principles within the breach materials. Next one are the instruments, hardware, software. Instruments that being used in this project are registered unmanned aerial vehicle or thermal drones such as DJI Phantom 4, infrared DJI camera, remote controller with DJI RTK app, and acoustic emission AE. The software like DJI GS RTK app and Playwolf Pro app were set up to link the thermal drone and infrared camera to the remote or flight controller. Hardware use a computer or laptop that equipped with DJI GS RTK app. The next one is the use of acoustic emission as an instrument to detect the defectness on the breach. The quick release of energy from a localized source or sources within a material or the transient elastic wave so created. As a result, an acoustic monitoring system primarily consists of involved two key components. First one, a material deformation that serves as the source of the stress wave. Second one is transducers that receive the stress wave that are derived from the original source. Emission from a secondary source. Primary emissions are those that come from within the material of interest, whereas secondary emissions are those that come from outside sources. The features of stress are intimately related to event detection wave. AE monitoring strategies can be divided into two categories, can be implemented on first, global, second, on local scale. Long-term and short-term AE breach monitoring can be classified based on the length of time that monitoring is required. We use short-term monitoring as it is more specific and it is usually the result of a survey. A short-term research to assess the structural integrity. The majority of classic AE sensors use piezoelectric elements that undergo transduction. The main job is to detect and convert transitory elastic mechanical waves into electrical AE signal. A large range of these sensors are now commercially accessible. Unidirectional breach monitoring in plane wave sensors and sensors responsive to in-plane wave modes may be useful. Preamplifiers available integrated with the sensor are integral components that improve the signal-to-noise ratio. These AE sensors are simple to install in existing machine and have no effect on the breach integrity or stiffness.
Next is about the type of data we use for this emission assessment. There are two types of data, which is foundation investigation data and surface data. Under the surface data, we can see three types of data collecting method. Firstly, survey control. Second, topographic map. Third is photograph. And under the foundation investigation data, there are two data type collection, which is geologic data and hydrologic data. Survey control. In this method, the control is required for coordinate system and existing land survey to assess the bridge defects. So, these control points will show coordinate and the monument of special control point established for the survey. There are two phases for the survey control. Firstly, feasibility phase, and secondly, specification phase. In the feasibility phase, they're trying to state the plane coordinate system or national coordinate system to integrate the effectiveness of this bridge assessment. Secondly, the specification phase that requires permanent horizontal and vertical survey control that can be established at the earliest possible time. Next, we're going to see the topographic map. That map can be detected or can be filed by the electronic file in AutoCAD. A computable format for topographic covering the structure site should be provided, and the details should be included in this map as proposed bridge location. Identify the existing site features such as overflow channels, channel changes, and provide a profile along the existing and proposed and central line exceeding at least 500 feet beyond the end of the bridge. Next is the photograph method. This color photographs shows the exact condition of the bridge, and then you can see the defects of the bridge from the shape itself or from the close-up view of the bridge features that may affect the designs. Next is geologic data. This data provides sufficient data to allow the designer to determine the type of foundation required for the structure and to identify major foundation problems. This data being used to determine the type of overburden and foundation condition some distance below the base of the bridge structure. Next is hydrologic data. This data contains annual periodic fluctuation of stream or river water levels. Also, it covers drainage area located upstream of the bridge site. Now we are going to see the methodology of usage of UAE thermal sensor and AE emission. For the thermal sensor, this image into in-service concrete beach decks using a low altitude aircraft mounted with an IR camera. This camera can identify delamination up to 4 cm deep and having wide deep ratio not less than 1.9. This camera form an image using infrared radiation differentiate apparent temperature variation using different color palettes. This camera can identify overheating equipment in the bridge during routine inspection, and if it's overheat, means that bridge has some defects. Next, we are going to see the acoustic emission in bridge defect assessment from integration. This AE is class of phenomena whereby transient elastic wave generated by the rapid release of energy from a localized source or source within a material, or a transient elastic wave so generated. The waves are captured when the component is submitted to an external stimulus such as high pressures, loads, or temperatures. As the damage grows in the bridge, there is a greater release of the energy from this AE emission. There are two testing methods: Percy transition and continuous. The transition method captures AE bursts that exceed a threshold and extract features such as peak amplitude, signal energy, and duration of the burst. This is mainly about the loudness of the substance or a thing that's been released. Secondly, the continuous method captures all the AE within a set time period, for example 1/10th of a second. The features such as average signal level or root mean square values are then extracted.
So for planning work, first of all, the selection of equipment. So for UAV, we chose IR thermal camera, which is FLRR View Pro, and we can see the table shown in this slide, the characteristic of the IR thermal camera. Next, we go to the selection of drone, which is DJI Inspire 1 Pro. So we can see also the characteristic on the table beside. Then we setting up the UAV borne thermal system. So first of all, this survey is carried out by the consultant, which is specialized in aerial photography, videography, and thermography. They also have completed the UAV training, IRT training, and has pilot license, as well as obtaining aviation insurance for high risk situation. Next, for planning work, as a supplementary NDE technique for base test in order to determine whether there is any additional damage. So we set it up 2 dump truck, which is 27 10 kilo for truck 1 and also for truck 2, and both trucks had a single front axle and a pair of rear axles. Both truck first and second axles has static wheel loads of around 40 and 47.8 kilo Newton, and SRT1 SHP1 is the labeling of the equipment for the test, as we can see the table. Next, this we can see the sensor arrangement for the 1, and then the sensor arrangement for the 2 and the T-trace. Next, so for the planning work of acoustic emission, For your information, acoustic emission is done in two different bridges, the pre-stressed bridge and also steel bridge. For steel bridge, we evaluate the monitor span structure behavior when subject to overloads. Comparison acoustic data collected during the normal traffic on the base, and then also for the overload passage. The span of grinders and bin column joints is chosen as potential damage area to be inspected. Two of the sensors were positioned under a grind around the base. Then, the process of work in UAV thermal sensor, the temperature reached 79 degrees Fahrenheit and the relative humidity was 19%. The wind speed was at 8 km per hour. Due to the beach depth's dry condition, the angle of the sun also is measured, and surface moisture content were taken into account when calculating the thermal contrast. Only 4 images were collected. Then this meant that the entire width and shoulders were photographed. The survey started when it hovered at height of 10 meters, and the thermal image provided by this instrument could reveal subsurface defects that are not visible to the human eye. They could also be used to identify the patches and the surface defects that are consistent with subsurface anomalies. Next, for process of work, acoustic emission for pre-stressed concrete pitch, the sensor was installed on the intermediate diaphragm around gilded seats on the first day of testing. Two sensors were placed 0.61 meter apart around the midspan of gilded 4, and the other two were placed on opposite face of a section of intermediate diaphragm close to the same gilded on the second and third days. The data were collected at the place to the bridge as well as the acoustic system. Enable real-time monitoring. We use DISP workstation and AAV software. Then the pencil lead brake, which is PLB, tests were performed close to all 4 sensors. Then the appropriate sensor spacing is usually set a distance where the AE amplitude drops to about 30 dB. The background noise level as suitable to sound level, 44 dB is also chosen at this stage. Next, for process of work, acoustic emission of steel bridge, we set 40 decibels, the best data as we said before, and then 2 trucks and 2 trailers weighing a total of 2,401.9 kilonewton man up the oversized loads for 200 kiloton. The trucks measured 6.1 meters, which is 20 feet in width, and 70.3 meters in length. No acoustic activity was detected in the absence of vehicles on the bridge. Next. Then process of data and output of UAV, we have 4. First of all, image pre-processing, which is exporting thermal image into process software, result in highly precise reference to the maps and 3D models. In image processing, the Gaussian smoothing filter is used to reduce noise with the software automatically determining the filter size. Then the histogram equalization function to distribute the intensity on the histogram, resulting in improved thermal contrast and distinguish illumination areas from surface feature. Then image registration, create a mosaic thermogram of entire bridge deck from the individual image. Then a stitching algorithm relies on comparing the pixel features in the group image and necessitated as a field of view. Then we choose the main function in MATLAB to calculate the mean for specified dimension of input data. Then another MATLAB code was written to identify the coordinate of each pixel in scale temperature data and arrange data in column order. Next. Image segmentation. Image segmentation was done by dividing an image into regions of constituents objects using the concept of point-based segmentation, object-based segmentation, and edge-based segmentation result in highly precise georeference to the maps and 3D models. This holding classification, there are two. Supervised and unsupervised. Supervised is the differentiation of data and a training process requires to produce a result, while the unsupervised is enable data to find its internal structures on its own, leaving the output unknowledgeable. K-means clustering, this method for statically data analysis to identify key features in the data to be classified, categorize the degree of similarity, and organize the data using cluster prototypes. And next, the delimitation maps, contour plotting the recorded temperatures in different levels of severity. As we can see, the pictures, green was used to reflect some concrete areas, while yellow for concrete, which need to be carefully monitored, and red for concrete areas needed to be fixed. Next. The process data and output for AE, acoustic emission, for pre-stressed concrete bridge, the load cases that generate the most acoustic activity on each day. Sensor 1 and 2 generated more acoustic activities than those recorded by sensor located near the lower of the diaphragm. The stress generated at the monitor joint as a result of the relative movement between the discontinuous joint at the beam bridge, and then the steel bridge. AE monitoring was carried out for two phases of loading. One is during nomography and then the overload passage. Sensitivity M4 at the beam column joints recorded higher AE activity during both loading phases. Signal amplitudes rarely exceeded 60 to 70 dB. It's rarely associated with significant structural damage, and then no physical damage was observed at the monitored joint after the test, only as a source originating from some relative displacement between the members on the bridge, such as the connection of bowl strip. And lastly, the acoustic activity due to the overload is higher than normal traffic, which included both light and heavy trucks. However, they are not significant enough to warrant a closer examination of the monitored area.
Next is accuracy and analysis. For UAV-borne thermal imaging can be used to delineate surface temperature of concrete structures from thermal infrared measurements. The defective areas in UAV-borne thermal imaging are commonly identified based on a visual interpretation of the captured IR images. Therefore, the thermal contrast developed from the concrete subsurface provided numerical values for the color contrast that were used in the present research to process data more effectively than simply comparing multiple images. For AE, intensity charts developed for the metal piping system were used for the quantitative analysis of data collected from the steel bridge. Upon analyzing the signal strengths obtained from this test in both loading conditions, only the data from sensor 3 located on the beam column joint during both load conditions could be plotted on the intensity chart. All the other signal intensity values have a severity value below 1. Most of that data points fell into the insignificant damage region, except the signal intensities from sensor 3 during overloaded. A signal intensity value lying in Zone C implies a defect that requires a follow-up evaluation. Here we cannot assign the high signal intensity to any actual defect due to various local uncertainties such as the movement of bolts, proximity to the beam column joint, etc. in the monitored region. Next. Conclusion. UAV. The remote sensing feature of UAV avoids traffic disturbance and mitigates risk associated with bridge inspections. The proposed methodology allows post-flight data processing. A robust analysis procedure was developed herein to detect and classify the severity of subsequent delaminations in RC bridge depth. In addition, the application of further developed image processing tools on the infrared thermal data, along with artificial intelligence-based approaches, can result in full automation of the analysis and augmentation of the decision-making process to make it more effective. AE. Currently available interpretation of the accurate AE data, both qualitative and quantitative, have also been discussed. A commendable effort is being made in the direction of improving AE systems, addressing the practicality and economic issues of implementing the technique of monitoring purposes. All in all, the application of AE in bridge monitoring reveals the potential of these techniques' versatility. The technological advances made in recent years have made the method more suitable for on-site monitoring situations. Next. Lastly is the recommendation. First is exploring the applicability of the automated IRT analysis procedure developed in this research to bridge soffit areas, correlating the findings of daytime and nighttime survey results, and studying the reliability of the developed system in detecting defects in the presence of asphalt overlays. Second is investigating the capability of applying an IRT continuous monitoring system for detecting the depth and thickness of delamination in full-scale RC bridge decks. Third is studying the characterization of IRT data using several feature vectors of the recorded pixel reading in the thermal images. For example, using the pixel shape and texture instead of relying only on the pixel numerical values. Fourth, it is advancing the application of other IRT image processing techniques along with artificial intelligence-based approaches to provide more objective classification of the detected delamination, categorize, and augment a faster decision-making process. Lastly, conducting intensive acoustic emission comparative studies on full-scale deteriorated bridge and quantifying the achieved result to motivate practical evolution of the employed methods and their wider implementation in bridge inspection.